What's up everybody, and welcome back to another SAT math video from the Scalar Learning channel. This one is part one of a 4-part series covering all of the critical concepts for the math portions of the SAT. This breakdown is done in accordance with the Khan Academy categorization of math topics. Khan Academy has placed the different topics of math on the SAT into 4 broad categories, and today we're going to cover the first category, which is the heart of algebra. Without further ado, let's jump into it. The first thing that we need to understand is that this entire section, and really every section, is all about variable isolation. So when we think about variable isolation, we think about getting the variable by itself so that we can actually solve for the value of the variable. And we do this utilizing something called inverse operations, which essentially means opposite operations. Okay, so for example, we have our basic operators here. We have plus, we have times, we have square roots, we have even a trigonometric function thrown in there. All of these have an opposite or an inverse operation. And in this case, for example, we see that plus is the opposite of minus, times divide, square root squaring, sine, and that is of course arc sine or inverse sine. There is a general principle that we have to follow when we're isolating variables, and that is remove numbers that are the farthest away from the variable first. So for example, if we look at this equation, we've got 2 times the square root of x divided by 3 plus 19 equals 21. I want to get that 19, I want to get that 3, the 2, and the square root all out of there so the x can be by itself as its own entity. So this is how we're going to run through and kind of attack this problem here. So first, what I'm going to do is I'm going to see what's farthest from the x first. Not that 2, not that square root, not that 3, it's the 19. So we're going to start by doing the inverse of adding 19, which is subtracting 19. I'm going to do it from both sides. We're going to subtract 19 from both sides. That cancels out, and of course now I'm left with 2 radical x over 3 equals 2. Excellent. Now, what's the next thing? Well, the 3 is the next thing that is farthest away, right? The 2 is on the same level. The square root is happening right directly to the x, so I want to get rid of that 3. Currently, the x is dividing that 3, dividing by that 3. So we want to do the opposite of division, which is multiplication. So now we're going to multiply both sides by 3. And in this case, these cancel out and we get 2 radical x equals 2 times 3, which is 6. Now I want to get rid of that 2, right? The square root's going to be the last thing we're going to get rid of. I want to get rid of the 2. The 2 is multiplying this quantity, so we're going to divide by 2. That's the inverse operation of multiplication. And I get square root of x equals 6 over 2, which is 3. And last but not least, we need to undo the square root. I need to get rid of that square root. What's the opposite of a square root? Is squaring both sides. So square root of x squared is just x, and then 3 squared is of course 9, and there's your answer. Next, we're going to talk about linear equations, and a linear equation is simply an equation of a line. So here are a couple examples on this graph of linear equations in terms of their formulas and what they look like. So here's y equals 2x, a very basic linear equation, and you can see that point 1 comma 2 falls on the line, and that makes sense. If I plug in 1 for x, I'll get 2 for y. Next, we have y equals x plus 3, and notice again I've called out that point -5, -2. So again, if I take that -5x value, plug it in for x, I get -5 plus 3, which equals the y value of that coordinate, -2. And last but not least, a little bit more complex one, we've got y plus 3 equals -3/4 times x minus 4. That again is simply just a line, and this one has a negative slope, so you kind of see it going down from left to right. Now, when we talk about linear equations, there are a few points and values that we have to be aware of. So these are the critical values, and these are especially important when it comes to word problems or interpreting linear functions. So I've taken one of the lines from the last example, and I want to identify these points. So the first thing we have to identify is slope. And what is slope? Slope is rise over run between any 2 points on the line. So here I've chosen 2 points that are easily identifiable, and to get the slope, I'd simply take the rise, meaning the distance I'm going up, over the run, which is the distance I'm going across, to get from one point to the next, and I'll go into more detail on that in the next slide. When we're talking about a word problem where we're trying to interpret a linear function, the slope value is always the rate of change. It's the amount that the y value or the final value is going to change every time the x value usually increments by 1. Now let's talk about the y-intercept. The y-intercept, as you can see on the graph right here, is where it hits the y-axis. Okay, so this is literally where it's hitting the y-axis. And the way we think about this when we're interpreting a linear function or a linear equation, it is usually our starting point, right? It's our starting value, our initial value. If we think about a gym membership where we have a fee that you pay to sign up and then a monthly fee, the monthly fee would likely be the slope, and the initial payment, the one-time fee, is going to be the y-intercept. And again, you can see that the x value of the y-intercept is always 0. Finally, we come to the x-intercept. So the x-intercept, as you can see on the graph, is where this function intersects the x-axis. And usually how we interpret this in a linear function or linear equation is it's the point of 0 value. It's where we're hitting 0. So for example, if we're talking about a linear function that represents profit, the x-intercept is going to be the point at which we have a 0 profit. Lastly, we can see that for every x-intercept, the y value will always equal 0. So if we have an equation, we're trying to find the x-intercept, just plug 0 in for y. Now we're going to talk about the different forms for linear functions. And first and foremost is slope-intercept form. This one you gotta know. It's tested extremely frequently on the SAT. So slope-intercept form is y equals mx plus b. Make sure to burn that into your brain. And in this case, the m is slope and the b is your y-intercept. So it means that when y is isolated and we've got a linear function, a linear equation, whatever number is next to the x value is going to be our slope value, which again was rise over run, and whatever constant is out there by itself is going to be the y-intercept, again, where this function crosses the y-axis. So to just get a better visual understanding of what the slope means when I'm saying rise over run, let's take another example where we have a graph, we have a line, and again, I'm choosing two arbitrary points. That's the beauty of it. The slope will always stay the same for a linear equation. It doesn't matter what these 2 points are, but I'm choosing two arbitrary points, and I'm just looking at, hey, that's the rise, that's the run. The slope is the fraction of the rise over the run value. And again, just to get more familiar with what the y-intercept is, it's that point right there where we're intersecting the y-axis. So now here's an example of slope-intercept form in action. Again, I've got the baseline equation y equals mx plus b. So let's say we have the graph of y equals 2x plus 3. So you'll notice the slope is that 2 value, and we can see the rise over run of those 2 points. It's 2 over 1, right? Which 2 over 1, of course, equals 2. And that b value, that blue value, is the y-intercept, and you can see it crosses the y-axis at 0,3. And you remember I said every time you have a y-intercept, the x value is going to be 0, and that of course is holding true here. Next, we're going to talk about point slope form. So this is another one that you've got to know. It's not as important as slope intercept form, but I would say to definitely know this form. So in this case, the format for the equation is y minus y1 equals m times x minus x1, and once again the m value is slope, and the x1, y1 values are simply the coordinates of any point of this line. You can choose anything and it'll still be a valid equation. Now here's an example of point slope form, and again we've got the graph up there and we've got the equation at the bottom. So I've got y minus 3 equals 2/5 times x minus 2. So in this case, again, that 2/5 represents the slope. It's going up 2 and to the right 5, right? That's always going to be the ratio, up 2 to the right 5. Even if it went up 1, it would go to the right by 2.5. So it's a proportional relationship. And then there, of course, is that coordinate that we see up there. That 2 value and that 3 value represents a 2,3 coordinate. And you notice that's a positive 2 and a positive 3, but in the format of the equation, we're always subtracting those values. So if it was a negative value, it would actually turn into a plus. If it were a negative 3 there for the y value, it would be y plus 3. Next, we're going to come to standard form. So what is standard form? Standard form is when a linear equation is written in this format: ax plus by equals c. To be a valid standard form, a, b, and c must be integers, and a must be positive. This doesn't mean that b and c have to be positive. This just means that a must be positive for it to be the valid format of standard form. So for example, if we look at y equals negative 2/3 x plus 7, that's in slope-intercept form, the equation written in standard form would be 2x plus 3y equals 21. Now I'm going to show you how we go from that slope-intercept form to standard form, how we get there. And essentially we want to think about isolating that constant. That's really what it's all about. So if I, for example, take this format, first thing I'm going to do is I'm going to add 2/3 x to the other side. So let's start up here. I'm going to add 2/3 x to the right side, and I get 2/3 x plus y equals 7. Okay, that's excellent. And then the last thing I need to do is I can't have a fraction here, right? I need that 2/3 out of there. So I'm not going to multiply by the reciprocal, which a lot of people think like, hey, I'll multiply by 3/2, get rid of the fraction. But that's going to create fractions here and here. So instead, I'm going to look at that denominator and I'm going to multiply everything by that denominator, which is 3. So I'm going to multiply this whole equation by 3. 3 times 2/3 is just 2x. 3 times y is 3y, and then 3 times 7 is, of course, 21. So that's how we go from slope-intercept to standard form. Next, we're going to talk about another huge topic involving linear equations, which is systems of linear equations. And that sounds really complicated, but really all it is 2 lines. Could be more than 2, but usually on the SAT it's just 2 lines. It's 2 lines and we're seeing where they intersect. So again, if we take this example of y equals 2x plus 1, that's the green line, and y equals negative 2/3 x minus 7, the solution to the system is that intersection point of -3, -5. So that's it. Again, it's just the intersection of the 2 lines and that particular coordinate where they intersect. Now, when we talk about systems of linear equations, what I previously showed you is how to look and solve from a graph. But we may not always have a graph, and we may not always want to make a graph because it takes a lot of time. There's 2 methods by which we can solve a system of linear equations algebraically. The first one is called substitution. So in substitution, what we're doing is, again, I'll take these 2 equations and we're going to substitute one into the other as long as y or x has already been isolated. In this case, both the y's are isolated in both the equations, so it makes it really easy to sort of substitute. So I can say like, well, wait a minute, since I'm looking for a point where these guys intersect and y already equals this, I'm going to plug this value in for the y down there. Their x and y's are equivalent at this point of intersection, so I can do that. So instead of that y, I'm now going to write 2x plus 1, and this equals negative 2/3 x minus 7. And now all I got to do is get the x's together. First, I don't want to deal with that fraction, so I'm going to multiply everything by 3, and I get 6x plus 3 equals negative 2x, right? Negative 2/3 times 3 is negative 2x. And then this times 3 is minus 21. So I will now add 2x to this side. 2x plus 6x is 8x. And then simultaneously, I'm going to subtract 3 from both sides. And so that 3 goes away. Negative 21 minus 3 is negative 24. Last but not least, we're going to divide by 8. And guess what? X equals -3. And this is exactly what we got when we graphed it and we looked at the coordinate. And the corresponding value on the graph was -5. Now we're going to do this, but we're going to do it algebraically. So what do I do with that -3? I can now plug it into either equation and solve for y. I should get the same value for both equations if I've done this correctly. So if I plug in a -3 into this, I get y equals 2 times -3 plus 1. That becomes -6 plus 1, and therefore y equals -5. So there we have an algebraically derived solution for this system of linear equations. Next, we're going to talk about solving systems of linear equations using the method of elimination. So elimination is actually my favorite. Whenever I can do it, I do this instead of substitution. I find it to be easier and a slight bit faster. However, there are certain situations where substitution is just the better option. But what is elimination? Elimination is where we take 2 equations and we kind of match them up and then add them together, whereby we're adding them in a way where one of the variables cancels out. Okay, so I'm gonna show you how to do this now. So again, I've chosen the same equations, and you'll notice that the y's are perfectly matched up, and they both have a coefficient of 1, and that's very important. But I'm gonna show you a different way to do this because I wanna focus more on the x's and show you the process of how we have to match up coefficients to properly eliminate in any situation. So I look at this and I've got a 2x here, right? Theoretically, I'd love to be able to have a negative 2x on the bottom, and I'm going to show you why. So first of all, how do I get a negative 2x on the bottom? If I multiply this entire equation by 3, watch what happens. I get 3y equals 3 times that is negative 2x, and then minus 21. Now I'm going to take my original, my top equation, which is y equals 2x plus 1, and I've got something really special. Now I can add these together. I can combine them. I can say 3y plus y is 4y equals, that's 0. So now I've canceled out one of the variables. I've got a single equation with a single variable. Now I can solve. And then I got negative 21 plus 1 is negative 20. All right. Now, how do I isolate? Simply divide by 4, inverse operation of multiplication. And I've got y equals negative 5. Terrific. And once again, this matches up with our previous answer that we got in substitution. To get the x value, I just take this negative 5 and plug it into either equation. I'm going to plug it into the top one. That feels easier to me. So then I got negative 5 equals 2x plus 1. By subtraction, we're going to isolate. I'm going to subtract 1 from both sides. Boom, I got now negative 6 equals 2x. And last but not least, divide by 2, and I've got x equals negative 3. So again, you can see whether we graph, whether we substitute, whether we eliminate, we get the same answer every time, which is a coordinate pair of negative 3 comma negative 5. Next, we're going to talk about inequalities. Now, inequalities are another thing that the SAT loves to test on, the College Board loves to test, and the same key exists. We're going to isolate to solve. So nothing changes here in terms of how we're applying our same methodologies. If we take this example of 4x plus 16 is less than 32, once again, I want to get my variable by itself. So as we get the variable by itself, what we're going to do is again move the thing farthest away from the variable first, which is at 16, and the opposite of addition is subtraction. So we're going to subtract both sides by 16. Now I have 4x is less than 32 minus 16, which is 16. Last but not least, divide by 4, get rid of that 4. And we've got x is less than, what's 16 divided by 4? That is 4. So once again, we've used variable isolation. We don't have a specific one solution. This is actually an infinite amount of solutions, right? Because it's everything that is less than 4 satisfies this equation, meaning 3, 2, 1, negative 100, negative 1,000,000, and so on and so forth. When we're dealing with inequalities, there is one rule that you've got to know that is tested pretty frequently on this SAT, which is that when you divide or multiply both sides by a negative, you must flip the inequality symbol. So here's a quick example of when you must flip the inequality symbol to get the right answer. So we've got this inequality, negative 3x plus 17 is greater than negative 7. All right, let's solve. Again, I'm going to follow the standard protocol, isolate. So first I'm going to get rid of the 17 because that's farthest away. Let's subtract 17 from both sides, and I get negative 3x is greater than negative 24. Terrific. Now I have to continue to isolate. I need to get rid of that negative 3. It's multiplying, so I'm going to divide. I'm going to divide both sides by negative 3, and we get x is, now here, negative 24 divided by negative 3 is 8. But wait a minute. Normally I'd say x is greater than 8, but because we divided by a negative, we have to flip the inequality, and I say x is less than 8. Now that might seem a little weird, but then you can try values out and plug them back in, and you'll see that it actually works. So for example, if I plug in a 7 here, I should get a true statement. So if I plug in a 7, that'd be negative 3 times 7, which is negative 21, plus 17 is greater than negative 7. What's negative 21 plus 17? That is negative 4 is greater than negative 7. Guess what? That's a true statement. Therefore, we know we've done this correctly. Now let's talk about how to graph these linear inequalities. Okay, again, linear inequalities is just like a linear equation with y and x, but we have an inequality symbol instead. So for example, if I have y is greater than negative 2x, the first step is we graph this just like the line of y equals negative 2x. However, because it's a greater symbol, not a greater than or equal to, not a less than or equal to, we have to start with a dotted line. So that is literally the line of y equals negative 2x, except for it's dotted because we're representing that it's greater than, meaning the line itself is not an inclusive solution, but certain values bounded by that line are the correct values, are the solutions. So when we say now we're going to graph y is greater than negative 2x, we need to shade because we need to cover that massive solution set of everything above this line of negative 2x. So when we see that greater symbol, we know we have to shade above. So you see how that shading is going up from the line. That's how you shade a linear inequality correctly. Now when we think about solutions to this linear inequality, we can see that 9, 1 is a solution. It's in that solution set. This is one of infinite solutions. And it works again because again, if I plug in 1 for y and 9 for x, I get 1 is greater than negative 18. That's a true statement. That just helps us verify or validate the fact that we've graphed this correctly. Here's another solution of 5, 5. And once again, if I plug that in, I get 5 is greater than negative 10, which is again a true statement. Now let's look at an equation where it's not greater than or less than. We've got an equal in there. So this is y is less than or equal to x plus 1. Now the line itself is also a solution plus all the values less than that line because again it's less than or equal to. So now again we graph a solid line here because it's less than or equal to, and that is the line of y equals x plus 1. Now where do we shade? Well, it's less than, therefore we shade below, right? So it's below. And here we see 2, 1. That's in the solution set. That makes sense. If I plug in 2 for x and 1 for y, I get 1 is less than or equal to 3, which is a valid statement. Here's another coordinate in the solution set, which is 5, negative 5. Again, if I plug in negative 5 for y and 5 for x, I get negative 5 is less than or equal to 6. Again, a valid statement. Now let's talk about systems of linear inequalities. Just like systems of linear equations is 2 or more lines, systems of linear inequalities consist of 2 or more linear inequalities. So again, let's go back to our initial 2 examples. We've got y is greater than negative 2x, where we're again shading above that line. Then we've got y is less than or equal to x plus 1, and we're shading below. Now when we have a system, we are looking for the overlap of the shading, and you can see to the far right, that dark purple section where it's both, we've got the red and the blue shading, that is our limited solution set. So we're looking for the intersection of those 2 zones. In this case, we see that 7, negative 2 will be a true solution for both of these linear inequalities, just like 8, 3. So if we were to plug these in to both of these linear inequalities, they would both be valid statements. Now just a quick note, if you're asked to assess a system of linear inequalities and determine whether or not a particular coordinate satisfies this system, I don't necessarily recommend trying to merge the inequalities like we do with substitution and elimination. Instead, what I recommend is just plugging and chugging, trying the answer. So for example, we can see that 8, 3, I'm telling you that's gonna work, but let's say they gave you a value out here. Let's say they gave you negative 2, negative 3. So we got a potential solution of negative 2, negative 3. Now, of course, I can see on the graph that it doesn't work, but assuming we don't have a graph, I'll verify it by just plugging it in and seeing if we get a true statement for both linear inequalities. So the first one, I'm going to say negative 3 is greater than negative 2 times negative 2. Right off the bat, negative 3 is greater than 4 is what we get. This is not a true statement, so I can see that that fails the test. Now, if I were to plug it into the second one, I probably would have gotten a true statement, right? So I'd get negative 3 is less than or equal to negative 2 plus 1. This gives me negative 3 is less than or equal to negative 1. This is a true statement, which makes sense because it falls in the correct zone for one of them, for the purple one, but not for the green one. So we always want to check with both linear inequalities to make sure that we get valid statements for both, and then if we do, it's a solution. That's it for part 1 of this 4-part series on SAT Math. I hope you enjoyed it, and if you did, please click that like button. And if you want to see more from the Scalar Learning channel, make sure to click subscribe. Thank you so much, and I'll see you in the next video. Take it easy.